Okay. Well, welcome to a short little addition to the physical chemistry video. This one will be incredibly short after the last one, which was incredibly long, but this one might take a little while to work through this problem. And that is essentially, how do we treat electrolytes, the chemical equilibrium equations with electrolytes? Last chapter, we looked at the equilibrium constant K is the product of all the activities rather than the concentrations. With the activities can then be split into the activity coefficients times the concentrations. So this is most often going to be used for KSB. So how does a solvent dissolve differently, knowing the fact that it's going to form ions and thus screen each other and then affect it? So we have essentially reapplying this, kappa is going to be the activity of the cation times power of the cation, activity anion times power of the anion, or essentially the concentration of the cation is power of the coefficient of the cation, concentration of the anion raised to the power of the coefficient of the anion times the activity, the average mean, or the mean ionic activity raised to the power of the total coefficients. So we have three different variables. So this we can relate together pretty easily. But this becomes a little bit harder. So how do we find these concentrations from our equilibrium without our without this? We have three variables. How do we find this and this in terms of this without one without the other? And so this becomes a really hard equation to solve. But we can solve this through iterative mathematics, where essentially we run this process over and over again, adjusting our activity coefficient until the equation reaches a consistent point. So we're going to start by assuming, what if, well, because in order to find the activity coefficient, we need to know the concentration. But in order to find this concentration, we need this activity coefficient. So we're going to solve this first one time, assuming the activity coefficient is 1, and then find our concentrations. Then, with that in mind, we're going to find the concentrations. Using those concentrations, we're going to find the activity coefficient. And then plug it in again and keep solving that and keep solving that until essentially till it approaches the same point. So we're going to start with silver chloride, assuming at 298. What is the concentration of silver chloride in a real solution? You need these equations where this is the average molality. This is assuming the molality of silver and the molality of chloride are the same. Now we can figure this out. So we're going to start by solving the concentration, and we're going to say concentration and molality are essentially the same. So I'm going to switch to Excel. This is actually much easier to solve in Excel than it is to solve on paper. So, okay, with that in mind, so let's start KSP. KSP, we have a constant there. So I'm going to write the KSP. This is equal to, so first, the V plus, let's write, let's see. V plus is always going to be 1. V minus, always going to be 1. The Z plus, always going to be positive 1. And the Z minus is always going to be negative 1. That's not going to change. But okay, so with that in mind, concentration KSP is equal to concentration squared times the activity coefficient to the power of 2. Well, let me write that down. So, and then our overall V is 2. So with that in mind, if we're solving for concentration, we have our KSP divided by 1 squared. 1 squared is 1. So we're going to square root this number. Square root this divided by, we're going to call it 1 power 2. So there gives us, I'm going to go a couple more decimals out. So there's our first starting concentration. I is going to be that concentration divided by 2 equals this divided by 2 times this plus this raised to the power of 2. This times, so this times this plus this times this raised to the power of 2. I need to put a multiplication factor. So because of that, it's just 1 squared plus 1 squared is 2 divided by 2. So the ionic strength has not changed. Now let's look at how that affects the activity. The activity is exponential of negative 1.173 times z plus, the absolute value of z plus and z minus is 1, times the square root of whatever this is. Oh, I need another parentheses. Okay. So the activity coefficient now is 0.995713. So let's plug this in. So with this in mind, this is now 0.995713 raised to the power of 2. And it's iterative, so it's going to work it through again. So now, actually, I'm going to undo that real quick and just, so this is just always be always 1. Always F, always 4, always F, always 2, always F, H, always 2, G, always 2. Just so that constants are held through. Square root of always H, always 4. Just this way, as I drag these 3 down, I can see how this changes when I change this. So now I can just simply grab this and replace it with that. Okay, so here's a problem. So this whole thing needs to be, we divide our B1 by our gamma squared before we square root it. So that changes it. I'm going to fix that right here. So that factors that down. So that is dropped by a bit, but that is, oh, so, okay. Here, I'll make sure. Yeah, shit. Okay, I want to make sure this is actually iterative. So, yeah, I'm not going to change. So, okay, there we go. There they've changed because we want it to keep factoring down. Keep factoring down. So this right there now becomes, so that's changed a bit. That hasn't really changed any because it's still plus 2 or times 2 divided by 2. But this is now dropped a little. Hasn't changed much. Hasn't changed much because we're square rooting this, that it's been a small change. Now let's try again. Break that down. Now we're square rooting instead of J4, it's J5. I can keep dragging this down and it'll keep changing ever so bit. But you notice now that the activity coefficient has not essentially changed, and this hasn't essentially changed. So our overall change has gone from 0.1316 to 0.13, let's say 13416 to 13474. So the actual concentration dissolved has gone up by a small amount. But of course, this is what? Silver chloride. This is a simple case. Let's try another situation. So I'm going to go ahead and copy this, but I'm going to have to modify this. Next one. Okay. So this is now, I want this to refer just to that B1. Yep. Okay. Okay. So this is for magnesium dihydroxide. So we got to actually change this, change this a bit because our KSP is no, or KSP is not, KSP is going to be magnesium equals magnesium, that hydroxide squared times, squared times, where's the times? Y to the third. So let's look at that. And because we're gonna assume the hydroxide is the same, is just double the concentration of that of the magnesium. So we're gonna say that this is, so X and 2X. So this is going to be what? 3. It's not square root. It's actually going to be, let's go ahead and, 3 divided by 4. And then we're going to take that whole thing to the power of 1/3, which is a cube root. So 1/3. So the actual concentration right now, 1.19 times 10 to the negative 4th. Let's see. I'm going to check my math. 5.61 times 10 root negative 12. I just want to make sure I've typed this in right. Okay, divided by 4, power of 1/3. Yeah, 1 point, yeah, that looks right. Okay, now our I is changed. if this is the concentration of X, I'm going to actually say, instead of this, I'm going to say, okay, sum of ions, I'm going to actually multiply by the molality. I'm going to say the molality of one guy is different from the molality of the other guy. No, I'm going to leave that in there. See how that, because I'm going to think the coefficient already takes into account that. So the V plus for magnesium is 1, but the V minus is going to be 2 because we have double that. The Z plus is going to be 2, Z minus is 1, and V is now 3. So looking at that, taking into account all those things, and so that's carried in. Average of those, see, we have a greater ionic strength than we would have predicted. Let's see how the gamma changes. The gamma is now 1.173, or not a gamma, or the gamma, the activity coefficient. Now it's not times 1, it's times 2, because 2 plus times 1 minus is the effect of 2, and square root of whatever I is. Effectively that. So activity coefficient first trial is that. So now we're dividing by, it's not I, we want to divide by power of third. So that's first trial, 1.12 times 10 to the negative fourth goes to 1.16. The activity coefficient is changed. We do it again. 1.69. Change a bit. You can keep doing this, and if you write the correct equation, you get to the point where it doesn't change any significant amount. If I went out more and more fractions, you'll see the difference. See, this one's different from this one on these units, but on that extent, it's not nearly as big of an effect. So, but, so that, let me get this. So, what that's essentially given us is that the concentration of a real solution has been affected by the 1.11 and a 1.17 essentially, and that's just for magnesium hydroxide. So, and so it's essentially where we can more accurately, iteratively approach a point where it's approach a point where it is well, approach a point where you get the most accurate of all numbers. So while this one doesn't have a super huge effect, you could see that if as these numbers increase, as you get greater charges, you're going to have a greater deviation to the point where you could see some effect, some large effect. But that's how you could work your way through these problems. If you get your activity coefficient to drop significantly, then you start to see a large effect, and that's something we have to start being concerned about. So, okay, that's all I wanted to share with you. It's not very long, but that actually ends up this chapter. So I know it wasn't long of a video, but I wanted to make sure we had some time to spend on the iterative approach. With that in mind, Wish you a day, a good day, and please like, please subscribe. See you later. Snoochie boochies.